Okay. Hi everybody, welcome to our next session on multimedia programming, this time about learning, machine learning for audio signals in Python. So this basically gives you the basics of how to use machine learning on neural networks in the machine learning context. So we will start with neural networks for detection, because that's kind of an easy application. And as, for instance, if you have an audio, you want to detect a certain sound, or if you have an image, you want to detect an object in this image. So we already saw how to detect an object in an image in our little examples using the Haar wavelets. So that's related in the application. So there's also a way of using neural networks for detection, and they usually have much better performance because they can be much more complex structures. Yeah, so first we will use Python PyTorch as the library or module for our machine learning experiments and implementations, and that's because PyTorch is quite widespread in academia and research because it's quite well documented and also more easy to debug, for instance, using the print statements. Yeah, so for that we first need to have a computer running on Linux, for instance Ubuntu Linux, as I have here, for instance as dual boot, or a Mac OS, which is also a Unix operating system. So that works too. Yeah, so as you know, you can install Ubuntu from this website here, or from a DVD, from a computer magazine like Linux Welt or Linux User, and install it by booting from the DVD or the USB stick, and then choose the install option. Yeah, so once you all have Linux or Unix, you can then go to this PyTorch website and install PyTorch. So here we just need to follow the instructions. Usually it detects your computer environment automatically, and you just need to copy the install string to a terminal shell in Linux. So here CUDA means a compatible NVIDIA graphics processing unit. Hence on laptops you usually don't have it, and you can choose none or CPU. Usually you also want to choose PIP3 as an installer and Python 3 for the installation. So we can check it out here. Let me click on it. We go to the PyTorch website, and if we then scroll down, here you can see the setup. So here is what it suggests. So we have Linux, correctly detected it. PIP is already set. Python is okay, but here you need to change it. So in my case, I don't have a graphics card from NVIDIA, so I just click on CPU, and then you see here the string changes. So here, depending on what I click here, we have a different string. So then I would just copy the string here, Control C, and then copy it into a terminal. So you would open a terminal like this, and then paste it in here, and then hit return to install it. So that should usually do the trick. I won't do it here because it's already installed. Okay, so after we installed PyTorch, now we can go to the experiments or the basics. So first, this detector. So for the basics of neural networks, you can also read the slides of our multi-rate signal processing lecture. And here you can see, when you open this one here, open in the new tab, you can actually see the slides where you have a little bit more detailed description about what's going on in neural networks here, which I won't do here. So that's something you can do at home. Yeah, but you have this link. So the simplest layer of a neural network is a so-called fully connected layer. If we have a one-dimensional input array X of length in features, so that's the name of the number of features that you have for this network, and a one-dimensional output array Y of length out features, then its function is simply a matrix multiplication with an addition of an array B called bias, followed by a nonlinear function called the activation function. Right, so this is the naming convention. So in PyTorch, the matrix multiplication and addition is this function, torch.nn for neural network, .linear for linear layer. Here you have the number of input features, so this is the length of the input vector it processes. Then here the size of the output vector, the length of the output vector, the desired output vector, and here the bias. In this case it's true, which means we do have it. And this computes this function here. The output Y is vector X times A transpose, and A is a matrix of weights. Right? And these weights, they have to be found by training. And then plus B, plus this bias vector B, which also contains coefficients which the training needs to find. Yeah, so here the T is the transpose operator for the matrix. The coefficients of the matrix A and the array B are called weights. They will be obtained using optimization, also called training. Yeah. So you can also see a more detailed description in this link here, and then search in that page for nn.linear. So it's actually quite a nice documentation here. Yeah, this is also called fully connected because the matrix A connects each input element, also called feature, to each output element or feature. Right? You have weights all over the place. From every input to every output we have a weight, and then they're all summed up. The input and output arrays are one-dimensional because of the full and fixed connectivity. If we have an image as input, we would just reshape it first into a one-dimensional array, for instance with view or reshape in Python. Right? Because here the position doesn't really matter. We just have data that comes out and data comes in and data that comes out. So the dimensionality doesn't really matter, and we can always shape it into this one-dimensional form. And if we desire, we can also reshape the output from one-dimensional to some higher dimensional using reshape. Yeah, often neural networks are used as detectors. In that case, each value in the output array Y would correspond to the output of one detector. And each detector represents one class. Yeah. So you would have an output. You can imagine this output is like between 0 and 1. And when it's close to 1, it's very likely detected. If it's close to 0, it's very unlikely detected. Yeah, this linear layer is usually followed by a nonlinear function, also called an activation function. So that's another term that you need to remember. For instance, the rectified linear unit function, which is applied to each output element or feature. So here you can see this function, torch nn.relu, in place false. This is just another option here. So you can apply this, and then the output would override the input. In this case, it's false, so the output would be a separate array. Yeah, so this applies the element-wise function, which is this. So rally of x is simply the max of 0 or x. Right, so if x is larger than 0, then it's x. If x is 0 or below, then it's 0. Right, so cutting off. Yeah, so this function limits the output to the non-negative range. This is useful when the output represents a detector. In this case, a value of 1 might mean detected with certainty, and a value of 0 would mean not detected with certainty. Here, negative values would make no sense. Right? If you interpret it like a probability, for probability you don't have negative numbers, so they don't make sense. Yeah, this is probably the most often used activation function because of its simplicity. Right. Yeah, often a slightly modified version is used, which avoids the vanishing gradient for negative values, which helps the optimization. It has a small slope for negative value and is hence called leaky ReLU. So you can see it. So here this function is called leaky ReLU, and you can see it also has this option for the negative slope, and here you can set a number for the negative slope. This is basically the gradient for the negative part of this function, and you can see it's non-zero, right? And that's the purpose of it. If you have gradient descent, you follow the gradient, but if the gradient is flat, if it's zero, there's no direction. So the optimizer doesn't know where to go. So it helps to have even a small slope so that the optimizer knows in which direction to go. Yeah, so here you also have a link to the description here. So actually you can click on it, right click in a new tab here. And then you can see here's the description. So here's actually the code of this ReLU function. So you can see it's all quite well documented. Going back. Yeah, so this basically applies this element-wise function. So leaky ReLU is max of 0, x, what we had before, plus negative slope times minimum of 0 and x. Right, so that's basically how it's implemented. Yeah, then there is the softmax activation function, and that turns the outputs of a network into looking like a probability function, positive and summing up to 1. So this summing up to 1 is new now. So ReLU was already positive. Leaky ReLU not necessarily, can be tiny negative. But here it's always positive, and also if you have several classes, they always add up to 1. So imagine you have like a detector of digits, handwritten digits from 0 to 9. Then you have 10 classes, right, from 0 to 9. And that means you have 10 outputs, one for each class, and each output gives you a probability that it is seeing this number. Right? It's all positive, and they all add up to 1, such that they really represent a probability. Yeah, and that's done by normalizing by the sum of outputs. So here you can see softmax of x. Actually here it uses an exponential function, so that always turns any negative number x into some positive number using this exponential function here. And then here normalizes to the sum of all outputs, such that the sum will become 1.
Logits.
Yes, exactly, logits. Yeah, so an alternative is the so-called sigmoid function. The sigmoid is probably one of the oldest activation functions for neural networks, which is differentiable everywhere, but is more complex to compute. This is the classic activation function, which is already used in early papers about neural networks, and that's because they modeled it after natural neural networks. So here, this is the sigmoid function. You can see here you also have this exponential function, but it's here in the numerator, in the denominator, right? And you can see here, if you have a large x, then this term disappears. This becomes very small, and you have 1 over 1 is 1. If you have very negative x, then this term becomes very big, right? E to the minus x becomes a very large number. And then you have 1 divided by a large number, and then it goes to 0. 0. Yeah. So basically, it limits between 0 and 1, but in a smooth fashion. And when you have x equals 0, then you can see here you have e to the minus 0, this is 1, so you have 1 divided by 1 plus 1 is 1/2. So in the middle it's 1/2. Yeah, so now an example, a Python example for a linear layer. So here we can see it. So here you can also read more about it. So the general shape of the input and output layers are this. So this is now the format that this layer expects. So first we see the in features, which you already know, right? That's the size of our vector that goes in. But now we also have this capital N, and we have the star. Right? So the star means any number of additional dimensions as required for any reason, for the data, for instance. And the output here is similar. Here we have the output features, we have a capital N, and then this additional dimension. This is also called the channels dimension. So for instance, if you have an audio signal, then mono would have 1 channel, stereo would have 2 channels, surround would have more channels. Right? So you can imagine this star here can be used for different channels of your audio signal. Or if you have images, say color images, then each channel could be connected to the primary colors, R, G, and B. Right? Then you could also use this additional dimension here for your channels. So N is the batch size, capital N, and so batch basically means you load part of your training set into your computer. So often when you train a neural network, you have large data sets, and often they cannot be completely loaded into the computer. And that's why you group them into different batches. And while you optimize, you load, for each optimization step, you load one batch after the other. So basically you cycle through them. And in this way you can limit the number of data that you need to load into your memory, into RAM. Yeah. Right, so here optimization is performed one batch after the other. Yeah, so imagine we have 2 input signals we want to detect, one increasing and one decreasing. So here, this is a very simple example, like 2 audio patterns, each consisting of 2 samples. Also be aware that the term sample is used as different meaning in machine learning than in signal processing. In signal processing, one sample is the sample time point, one value. In machine learning, a sample is an example. So it could be an audio file or an image that would be the sample. So that's also something to keep in mind. So in machine learning, each would be one sample here, but in the signal processing context, each contains 2 signal samples. Right. Yeah, and then we can assemble the 2 signals into a 2-dimensional tensor, a matrix, where each signal is one row. So here first signal, here the second signal. So now we want to have 2 detectors, one for the first signal and one for the second signal. And the desired output of the first detector should be 1 for the first signal, x0, and 0 for the second, x1. The second detector should output 0 for the first signal, x0, and 1 for the second signal, x1. The desired output is called the target. So we can now specify what our desired output is. Right? And that's also typical for optimization problems. You want to minimize some distance. Right? And for that we need to have a target. And then we can compute the loss or some objective function which we need to minimize. Yeah. So we assemble the desired outputs or target in a matrix where each detector corresponds to one row. So here, this is now our target. So here's the first detector. First row is the first detector, and second row is the second detector. Right. So this is what we want to have if we give it our test or training set. So the training set in our case is just this one matrix. Right. So in this case, it's not big data; it's very small data, just to show you the principle. Yeah. So then we apply the computation for our linear layer. So we now need to find the weights, the coefficients of the matrix A and the bias B, such that the desired output Y is approximated given our training set X. So X here is our training set, Y is our desired output, and B here and A are the coefficients which we need to find. Right. Yeah, so in this simple case we can actually find a closed form solution, which you can see here. So B would be 0, and A transpose would be x to the minus 1 inverse times y. Right, so this would minimize the error. In this case, we actually have enough. Yeah, we have enough coefficients to actually perfectly reach our target. Right. So if we now have more samples in our training set for x and y, we get tall matrices. So we cannot really invert this x here. For instance, we would add another input, x2, for which both outputs should be 0 as a target. Right? It should not be confused by some new unknown input. Yeah, and for these non-quadratic matrices, we can compute the pseudo-inverse, which minimizes the mean squared error between the network output and the desired output. Yeah. Have you heard about this pseudo-inverse?
Yeah.
Good. So this is basically what we compute here. So again, same formulation here. So we drop the B, the bias. Yeah. So we then multiply both sides with X transpose. And then this becomes a square-shaped matrix, which we hopefully can invert, and then bring this one here on the other side, and this is then the solution. Yeah, so this is the solution for the mean squared error. So keep in mind that this is actually a specific loss function, this mean squared error. Yeah, so that this does not include the bias array B, which might lead to better approximation. It also needs the mean squared error. Depending on the application, we might want to use a different error measure, also called the loss function in machine learning. Right. Yeah, so this is actually also a simple and very widely used loss function, this mean squared error. And in PyTorch, this is the function MSE loss. So here you can see it. It's part of the Torch module, Torch neural network. Here you can specify size average if it sums up or it averages. And some more options here. So when you do the optimization, you specify what kind of loss functions you want to use for optimization. Yeah, for detectors of different classes, usually the so-called cross-entropy loss is used. So unlike what we just used, the mean squared error, usually for detection purposes we use cross-entropy use. And it creates a distance or divergence functions between two probability distributions. So here the probability distributions are the target distribution, probability 1 for the true case, probability 0 for the false class. And the distribution that the neural network generates, a predicted probability for each class with high probability value for the class that the network thinks is at its input. Yeah, so for this you need, this is basically going back to our softmax function, right? We have probabilities as output, and we want to maximize the probability for the correct class, right? So here you can see it. This is the loss function for this detection, cross entropy loss. Again, with a few options. So the options are usually not so important. They usually just affect the data representation. So sometimes it's good to keep that in mind, because if you have wrong data representations, you get problems. Yeah, to obtain a better solution and include other loss functions, in general, numerical optimization is used to find the weights of coefficients which minimize a given loss function. So observe that the loss function produces a single number or value for a given training set and given weights. Right, so we have our training set, we have our weights, and then we apply the loss functions to the output of our neural network, and we get a number. And we want to minimize this number by updating the weights. Right, so we have several optimization iterations, and each iteration tries to reduce the loss for the next iteration.
Yeah, it's just a scalar.
Yeah, exactly. So we need a scalar because we need to have this bigger, smaller relationship. Yeah. So the weights are then updated during the optimization to reduce this loss function. So here you have another link for the optimization, and I think I need to update this link. Yeah, common optimizers are stochastic gradient descent, short SGD, and adaptive moments, ADAM. So those two are probably the most used optimizers in machine learning, and you can specify it in PyTorch which one to use. Yeah, after we obtain the weights from the optimization, we have to see if it generalizes to other examples or just works on the training set. So for this, we have the validation set containing new input and target samples. This is used to modify the neural network structure until it performs on new samples or examples sufficiently. Right, so first you train it, but then you have to check how good it is in generalizing. So, yeah, once we have a good neural network structure, we test it on the test set, another set with new samples or examples to test the performance. So we actually have 3 different sets, right? Training set, validation set, and test set, to avoid so-called overfitting. Right? This can easily happen if, for instance, we have a very large neural network with many coefficients and maybe not such a big training set. Then this network can basically learn this training set. It can identify each entry of this training set and produce a corresponding output. And that's called overfitting, because if you give it something new which is not in the training set, it gives nonsensical output. Right, and to avoid this, we have those 3 different sets. Yeah, so here's also a simple tutorial with a regression example. So let's see if that works. New tab. Yeah, so the link is still there. And here, this is from Towards Data Science, quite a nice web page. And I think it has nice pictures, so you can see the regression model. Y equals A plus BX plus epsilon. So here you have a data set, and you want to put a linear function to approximate it. Yeah, so you can see it. Here you have generated data for training. Here generated data for validation. So you can see here, this is noisy data from this function ax plus b. Right, so you can see you had a plus bx, actually plus epsilon some noise. And then this is what you're getting. And then you apply training and this mean squared error loss. So here you can see this loss. And you can see it computes gradients from this function. This is what PyTorch does internally. So actually then we don't need to do it explicitly. Here it's done explicitly. And here we can see the update step. So here we can see we have this eta, which is the learning rate. And then here we have the gradient. So this is the mean squared error. Derivative with respect to a, the coefficients. Right, so here the coefficients a and here the coefficients b. So this derivative is a vector which is called gradient. Yeah. So you take this function, this one-dimensional function, and take the derivative with respect to each unknown. Right? And each derivative is one entry in this vector. And this vector is called the gradient. So then we can use this gradient for updating the coefficients. So basically here the new a is the old a minus a part of the gradient. So basically you follow the gradient direction down to make it smaller the next time. Here same for the b. Yeah, so this eta here, this learning rate is actually also something critical. You want to make it large to have large convergence to the minimum, but you don't want to make it too large because you can overshoot the minimum and then you get oscillations or even divergence. Right? So sometimes it's actually worthwhile to start with a large learning rate, and during the optimization, during training, you reduce the learning rate to get a more precise convergence for your solution. Yeah. Let's see. We get some nice pictures here. Not really. Yeah, so this is something for you at home to read more closely. Yeah, because here we have another Python example program. So we start our program with importing the PyTorch library and setting the device where we select CUDA only if we have a compatible GPU. Right, so you can see we import Torch and also the neural network module, and here we set the environment variable for the device. So in my case, CPU. Right, so usually we'll have CPU because when you're on the laptop, you don't have CUDA, usually. So then we define our neural network with a linear layer and a nonlinear activation function, which we can comment out on the forward function if you want to test the network without the activation function. So this is done as a class, such that a network is an object which can instantiate, initialize, and which we can instantiate and initialize in the main part of the program. Right, so here, this class basically defines the structure of our neural network. And here in the init, we set usually the dimensions. So here in this case, there's not much going on here in the init, and except for setting up this one neural network layer. So here, self layer 1, so this is part of this object. We have neural network sequential. So sequential means we have one layer after the other. In this case, we just have one layer, and that is this linear layer. And here we need to specify the number of input features. In this case, it's 2. Then the number of output features, also 2, since we have 2 classes. Bias, now we allow the bias here. We set it to true. Yeah. So here, this generates a fully connected linear neural network model, one layer bias linear activation function. And this object returns a trainable object. Yeah, and here now, if you want, we can have this nonlinear activation function. So in my case here I have a leaky velo, this activation function. And this is all part of the initialization. And then we have this forward function. And this is actually used for inference. Inference means it computes an output for a given input, as opposed to training. Right? In training, we update the weights. In inference, the weights are fixed. The coefficients, all coefficients are fixed. We give it some input and compute an output. And that's done with this forward function. And here we can see it applies our first layer to X, the input. And if we want, we can also apply this activation function to the resulting output. And then it just returns it. Right. Yeah, so in the main part of our program, we generate the data for training and validation. So here, the main part. So first, we need to know that the input needs to be of the type torch tensor. PyTorch expects this torch tensor data type. So it needs the indices or dimensions, badge, sample, features, or signal dimension. So that's the last one. So here we have one badge. We have 3 samples, and we have signal dimension is 2. Yeah. So then this is here our training set. This is our torch tensor. So here we can see it's a Tor matrix. Each row contains a pattern. And here this is the pattern where both should be, output should be 0. And yeah, here this is shaping it according to the dimensions, adding the first dimension for the badge. So here it adds this first dimension to it. Our non-existent badge, because since we only have one badge. And then we make the target, which contains of these rows. So here the detector for the first row, the detector for the second row, and here both should output 0 for the last one. Again, adding this badge dimension here. Yeah, and then we convert it to the torch tensor format. And then we have xval and yval. Yeah, for this is for the validation set. So here you can see now the x is slightly different. You can view this as, say, a noisy version. And you still want to have the same target. So it still should detect the first one if it's slightly noisy, and same for the other ones. So here, instead of a 0, I have a 0.5. Yeah. So observe that the validation input contains, data contains a scaled version of the training set. So now we instantiate the model, define the loss function and the optimizer. So here now you can see model becomes now our desired neural network. So here we set it up to device. So here it also knows where to put our neural network. So this neural network now becomes set up in the CPU. And next we define the loss function. Here loss function is this object here, or this object becomes the loss function, MSE loss. And then we define the optimizer, and here you can see how we do it. Optimizer equals torch optim sgd. So again, this is an object which we now use to instantiate our optimizer. And here we can also specify the learning rate. So here I set it to 0.1. And you can also see that it works on the model parameters here. So you can see model is what we just instantiated, and it has the parameters here as a function of this object. Yeah, so it's actually quite simple, this setup. It's basically all object-oriented. The model becomes an object. The loss function here is now a function. And the optimizer here is also an object which references to an object in the model. Yeah, now we can let it run. So here we have a choice of two optimizers, ADAM and stochastic gradient. In this case here, you can see I have both here. We can try which works better. Right. Both should work actually here in this case. Next, we can let the optimizer do 10,000 update iterations called epochs. So here we have a for loop for the training, epoch in range 10,000. So it's quite a lot, right? We let it run 10,000 times, this update.
Small data set, so it's okay.
Yeah, right, should be okay.
Yeah.
So here we can see it starts with running the model for the given input. So X would be the training set here. And we have ypred, that's the output of the model for our training set. And then we can compute the loss function between the obtained output and the target output. And that's the number here. That's now our loss. And then we can also display this loss. I do it every 100th epoch here. It prints the epoch and then the loss number, so that you can see how it goes down. Right. And then here, next step is the optimizer, which is now computing the gradients. First, it sets the previous gradients to 0, and then it computes the loss backward through the layers. So here we just have one layer, so it's trivial. So it computes the new gradients, and then optimizer step, it applies the step that we just saw with this learning rate. Right. Yeah, so that's basically all in this for loop here. So finally we print out the results on the training set and the validation set and the obtained weights. So here, now we have this optimized model, training set input, predicted output, and now we can see it. Actually, since we have a small data set, we can easily print it. Now we can also compute the loss and print the loss on the training set. And more interesting probably is here the validation set. We take this validation set, compute the output, print the output, compute the loss, and print the loss. And finally we can read out the weights from our model object using the function stateDict. Right, so this lets us get the weights which we obtained, which is quite practical, and then we can take a look at it.
We essentially put the model to the evaluation state before predicting, correct? Such that the weights are fixed.
Yeah, so after training, the weights are fixed.
Yeah,
and then
we put model.eval.
Yeah, and then we apply it to our validation set to see how well it generalizes. Yeah, so this is actually an important test, as I said, because it can easily overfit. Right, so, and if we're happy, then we can take our weights, take a look at the weights to see if they make sense, and if we're happy, we can also take that weights and say implement it into some embedded device where this neural network runs without needed to be optimized. So the inference part is often not so difficult. What's difficult is the training. Right? For training, you need big machines, but for inference, for letting it compute something or detect something, it just needs to have the neural network with fixed weights implemented. And that's fairly easy. For that, you just need to have the weights.
Yes.
So here we need PyTorch to do the optimization. But we can also implement the neural network in a completely different framework and just read in the weights that we obtained here. Right? That's why it's important to have a way of obtaining the weights. Yeah, and this program which I showed you is stored in the file pytorch.linear.py, and we can execute it in the linear terminal shell with this command. So first, let me check if you find. So we can download it. Yeah, so here you have the Python examples. Yeah, and it only contains this one file. So we can click on it, download it. So I put it to downloads, now home. So now downloads, and then we can open a terminal window. So let's see if we have it. PyTorch star.py. Yeah, so pytorch.linear is here. So we can copy it. Oops. Copy it and then open gedit to take a look. Yeah, so you can see it now in gedit. And this is basically what we just saw now in this file. I guess you recognize all of it. Yeah, do you have it?
Yeah.
Yeah. So if you have, if you too. So if you all have it, then we can let it run. So we can say Python 3. Yeah, so you can see it. It's actually fairly fast, right?
Yeah, it's just one.
Yeah.
Is it?
Yeah. So here you can see here the shape of our data set, training set, target. We defined the loss function, we defined the optimizer, and now here you can see the loss function, and here's the epoch. And you can see it begins with 0.5, that's the error, and then it goes down to 0.1, then 0.003, then 0.0007, and then it becomes very, very small, very fast. So already after 700 epochs or iterations, we are at 10 to the minus 6 roughly. And then still goes a little bit lower, but say after 1100 or so, there is not much change anymore. So it stays more or less the same. Yeah, we still have some small improvements here in this third digit, but since it's so small already, 10 to the minus 6, it doesn't really matter so much here in our case. Yeah, so here you can now see the output for the training set. So ideally this should be 1, 0. Right? And you can see this is practically 1 and this is almost 0. Here this should be 0, 1 again.
Yeah.
It's almost true.
Almost, yeah.
I guess for all practical purposes this is fine. And then the last one here should be 0, 0. Yeah, it's also 10 to the minus 5 is basically 0. Right. So it's just a little bit different here on the validation set. So here again, we want to have 1, 0. And here we have 0.2 and minus 0.05, which is kind of strange, right? But that's because, yeah, why do we have a negative here now?
That's because we have leaked value under activation.
No, it's because we don't have a activation function. No activation function at all.
Yeah.
Right? That's why we can have negative values here.
We are typically commented out in the model
Yes.
forward.
Yeah. So that's what we can try next, applying the nonlinearity. So here, small negative number. Also, the positive number is not so big, right? So here you would say, doesn't really work so well. The next should be 0, 1. Same effect here. 0.1 is not really close to 0, right? And the last one, this is basically 0, 0. So the loss on the validation set here is 0.23. Right? So loss on the training set here, you can see was 10 to the minus 6. 4 times 10 to the minus 6. Loss on the validation set is 0.2. So many orders of magnitudes higher. So we wouldn't be happy with this result.
Yeah, not even data.
Yeah, and also lacking our activation function. So this is the next we can try. So we can now oh yeah, it actually does have a leaky relu here. Interesting. Let me try to comment this out and see what we get. So let's try it again. So now I have really no activation function. So actually you can now see it's even smaller, 10 to the minus 12. So here you can see 1, 0, yeah, 0, 1, 0, 0, that's fine. Then here validation set, 0, minus 0.5. Not so good. Here, minus 0.5, 0, and here, minus 0.5, minus 0.5. It's not really good, right? It's you cannot really interpret this as probabilities. So, let's try softmax. Let's see what softmax is doing.
And activate for the output as well?
Yeah. So activation function and then using softmax. So here in the init, it just gives us this function. It's part of the model. And then in the forward, we need to actually use it.
Yeah, but softmax, we would never get negative values, right? Because
yes.
It is normalized probabilities.
Yeah, good point. So softmax should be always positive. And it should always be probabilities, meaning it adds up to 1. Yeah. So that should solve our problem of having minus 0.5.
Indeed, yeah.
So let's try. So now with softmax. Oh yeah, you can see it converges much slower, right? 0.8. Interesting. So it doesn't really get small. But here, training set. Kind of okay. 1 is very small 1 is okay. Oh, that doesn't look good. 0.5, 0.5.
I think with softmax we get the anomalous probabilities. We have to have a threshold such that it says that this is 1 and this is 0.
Yeah.
So in that case of white training set, it has to be, if the threshold is greater than 0.5, then it is 1 and 0.
Yeah.
Something like that.
Yeah. Right, so basically here, in this case, the output means it's not sure what it is. So 0.5 could be it's either.
Yeah.
Right. Yeah, but of course it would be nicer if it would be 0.
Yeah,
right?
We could typically set the threshold such that it is...
Yeah, you could. But you could also have a nicer network which can actually make a better prediction, I guess.
Stacking more layers.
Yeah. So when you have a new input, it's okay if a class detector says I don't know, but it's better if it says I'm sure it's not. No. So let's check the validation set. So here we have the loss of 0.09. So it's actually not too far from the training set. so that looks good.
Mm.
Then here we have 8.8.1. No, it's not too bad.
0, 0, 1, 0, 0.
Yeah. So this also doesn't look too bad. And here is the same thing. It doesn't really know what to think about this unknown or this middle thing. So for the training set, it is maybe not as good as before, but for the validation set, it's actually better.
Yeah.
Right, so here it shows that using the softmax gives us better generalization. So that's also an important property here.
But the third sample could be 1, 1 or 0, 0, right? It could be anything, typically.
Well, what we want is really what we have in our target.
It's 0, 0.
Yeah. So do we see it here? No, we see it in the setup here. So this is what we want, 0, 0.
But the neural network output has close to 0.5 and 0.5.
Yeah.
But in that case, it could be 1, 1 as well, but we do not know.
Yeah, so this is basically the limits of our possibilities of our small model.
Yes.
Right. So that's also a trick with finding the right structure for a neural network. Right? The neural network structure needs to be suitable for the data and the task. Right? So, if you make this model too small, it cannot find the best solutions. If you make it too large, you get overfitting.
Yeah.
Right. Yeah, and that's kind of an art. So it's still not really a science, but it's an art to get a feeling about how you have to choose the neural network, what type, what size, what depth, what breadth. So there are actually many so-called hyperparameters which you need to choose, where you need to develop a feeling about what it needs. There are also approaches where those hyperparameters are part of the optimization. Right? They're actually tools which try out different networks, but that might also be tricky and might take a long time because it needs to optimize different versions and then find out which works best. So this is actually a tricky problem to choose the right structure for the neural network, the right architecture and size. Okay, let's go back to the slides. So each time we execute it, it actually starts with a different random initialization. So the first time we run the model, it has random coefficients. The weights and the bias are just random numbers. And that's where it starts from. And hence, each time we get a different route to the optimization, or the optimization takes a different route, and possibly slightly different results of the optimization. If you get very different results, that is a sign that the optimization got stuck in a local minimum. Right? So usually, when you let it run several times, you should get almost the same solution. If not, then that's the sign that you have a local minimum. And that can easily happen because, particularly if you have large networks and nonlinearities, activation functions, then you have plenty of local minima where the optimizer can get stuck. And that's also why ADAM, for instance, has this built-in momentum. It's called momentum because it continues to walk in the same direction even after it reaches a minimum in order to overcome small local minima. Also, another trick is to play with the learning rate. If you see it get stuck, you would increase the learning rate in the hopes that it would jump out. Or sometimes if you see that it's getting good but very slow, it also is worthwhile to reduce the learning rate in the hope that it then converges better. Right, so here experiment 1 is where we have no activation function and the SGD. Right, we didn't try the SGD. Did we try the SGD?
I think we used SGD.
Did we?
Yeah, it's atom that we didn't use. In the main bucket, yeah.
Create object, mean squared error loss.
Yeah.
Oh yeah, SGD. So now we can try Adam. So uncomment Adam. And let it run again. So this should basically get us the same result. Let's see.
There are more sophisticated optimization ideas as well, right? Something like
yeah, there are many different optimization algorithms, but the ones here, the SGD and the ADAM, are the most popular. But yeah, you're right. So for some problems, other optimizers might be better. So it's worthwhile to try out. Particularly if you have very non-convex functions to optimize, where you have many local minima, then it might be worthwhile to look for something which uses no gradient, for instance, like black box optimizers.
But then we typically convert the optimization function to be a convex and then solve it for ease, right?
Yeah, that's also a possibility, to make the function more convex.
Yeah. Much more problem-free.
Yeah. So here we can see the result. Actually, this looks somewhat better, right? This is very close to 1 and this is very close to 0 on the training set. Here also quite close to 0, quite close to 1, that's good. But then here for the unknown, 0.5, 0.5 again. And the validation set, this looks pretty decent, I think. Also this one looks pretty decent. This is kind of so-so. Yeah, so it seems also here that ADAM gives us slightly better results than SGD. Yeah, so that's also probably why ADAM became probably the most popular optimizer. So also in my experiences, it usually works best. Okay. Yeah, so this is the printout that we might get. And it's kind of interesting that here we get the 0. So this actually looks much better, right, than in our example. Interesting. Why might that be? Looks pretty much the same, right? Yeah.
So, leaky value with SGD,
Leaky value?
With SGD is what that is used in the slides.
And SGD, I think this is what we tried first. And which loss function?
The loss function is MSE.
Ah, yeah, okay. So,
experiment 1.
yeah, and I think we already tried that, right? Yeah, so loss function, MSE loss. Oh yeah, maybe we should use the cross entropy loss. Yeah. The cross-entropy loss does not really fit here because it needs exactly one class to be true. Oh yeah, right. That's a good point. So here we have one case where neither class is true.
Exactly.
So that's, yeah. So that's actually this tricky class where neither is true. And cross-entropy wants to have, always one class has to be true.
Yeah.
So that they always add up to 1. Oh yeah, and which reminds me, that's also the case why with softmax we get the 0.5 and 0.5 because they need add up to 1.
Yeah.
Right. So that solves that puzzle. Right. We have this 0.5 and 0.5 because this is the case where, which is really not covered by the softmax assumptions.
Yeah. So essentially this becomes a classification problem from a regression problem typically.
Yeah. So let's see, mean squared error, okay. SGD. So now we can run this again, see what we get. Yeah, so now indeed we have those two very small again, but then this generalization, so-so, 0, but here the other detectors are not so great anymore. Right? In this case here, the validation set, the detectors don't work that well anymore. You can see here it's 0.38 for the true, and here it's 0.2 for the true. So the generalization is not so good here. So you see it's tricky. Right? And even such simple cases where you have a detector and you have a class which should appear in none of the detectors, it's actually tricky to design.
Yeah.
So from the probabilistic view, is probably you have a detector, and if it's unknown, you have a 0.5, which is also kind of unsatisfactory because actually you could clearly say this is not part of our class. Right.
I tried softmax with binary cross entropy, and we are stuck with the same problem of finding the last target. It's still a problem.
Yeah. Okay, so so this is what we got. Validation set. Here it's also not so great. So here 0.5 on the validation set. So there's actually quite a big loss. Right? It doesn't really work on the for the generalization. So, experiment 2 was now including the leaky reload, which we already did. So with leaky reload, we already get much better performance for our validation set. Here with a loss of 0.1. Then we can also try relo instead of leaky relo. That's also interesting. Has a constant 0 for negative values, and hence we have a vanishing gradient. And this vanishing gradient is also an important problem in training. Particularly when you have large networks with long dependencies, you easily have vanishing gradients, and then they easily get stuck. So we can try that. So going back to our code here. And here instead of leaky relu, we now take the normal relu, the non-leaky relu. Here stochastic gradient descent, And now let it run again. Yeah.
Okay chances actually.
Huh?
We get okay chances, for example, yeah.
Yeah, look at the loss.
Oh, okay.
So here, during the first 100 iterations, it made some progress,
Yeah.
but then it got stuck. Right? So all the 10,000 iterations were useless because we are stuck in one point.
Yeah.
Right? So that's not good. It's a waste of time. So then you can see here also the performance on the training set. 0, 0 basically.
Yeah.
0, 0, 0, 0. So it's useless. Same here for the validation set. Again, you can see what big difference the loss function makes.
Yeah.
It's really important. So even this tiny change from leaky reload to reload makes a huge difference.
Choice of activation function indeed matters.
Yeah. Yeah, activation and also the activation function matters, like for softmax, for instance. Right. So all those nonlinearities, which is usually not covered in standard signal processing. So in standard signal processing, nonlinearities are something mysterious, more or less. And they appear now here a lot, but they are still kind of mysterious. Right? Because they have sometimes unintended consequences, like here, this little leaky part of the relu. It also shows that the optimization sometimes is not so easy. You need a useful gradient here. Yeah, so you can see it's getting stuck. Yeah, so it gets stuck at this loss function, 0.33, and the cause is this vanishing gradient of the relu function in the negative input range. So that can have a big effect. So here would also be a task. Generalize the pattern detector to a signal detector like for code division multiple access, where you have two different patterns for logical 0 and 1. Make the detector such that it detects a pattern only at a given position in time, so when you shift through it, that you only want to detect it once, but not at others, and not when the other pattern or general other patterns are present. So this is actually, again, this problem. Sometimes you want to have no output, right? And that's difficult to get. Yeah, we assume that our received signal is shifted through our observation window. Train it on the data set and test it on another data set, as we just did. So this is actually a little bit more practical application, which you could use, for instance, for code division multiple access, which is a communication scheme where you represent ones and zeros, each one and each zero as a particular signal pattern. Right? And usually you do it in such a way that each transmitter get its own pattern pair. And in such a way that each pattern pair is almost orthogonal to other stations' pattern pairs, so that the detectors don't get any output from those other pattern pairs. Right. So again, you have patterns where you want the output of your detector to be 0. And that's actually difficult to optimize. Yeah, okay. Yeah, any questions at this point?
No. We'll try to do the task and let you know.
Yeah. Okay, then thanks for your attention and then see you next time.